Let's talk about conditional probability. This is a super important concept for us, and it's going to play an important role in terms of applications for inference and decision making, but it actually plays a fundamental role in all of probability. And the important thing to remember is that it's very counterintuitive at first, and it's really important to rely directly on the definitions rather than any intuition you might be bringing into the course from any other experiences you've had. Okay, so whatever ideas you might have about making inferences, I want you to just set them aside. And we're going to go to the definition as quickly as we can, and then try to rebuild our intuition from there. Let's motivate this with some engineering examples. Okay, so first let's start with a motivating question from electrical engineering. All right, so let's say that I've observed a radar signature, and I want to infer how likely is it that there is actually an aircraft approaching the airport. For biomedical engineering, let's say I test for a disease and the test is positive. What's the likelihood that the patient that I've tested actually has the disease? And for mechanical engineering, let's say that I have taken a set of structural integrity readings and I'm trying to infer what is the chance that the bridge that I've measured fails in 5 years. So what's the likelihood that I need to do some serious work in the next couple of years? Well, okay, I told you to ignore your intuition, but let's first just see what your intuition is like. So let's do a simple example. We'll roll a 6-sided die, and I'm just going to tell you that the outcome was even, all right? And then I'm going to ask, what was the probability, knowing that it was even, there was actually a 4? And intuitively, we can guess that the probability of seeing a 4, given that the outcome we know is even, that's 1/3. And that's right. So how did we get this? Let's unpack our reasoning a bit. There were 3 possible even outcomes, of which 4 is one, and all of the outcomes are equally likely because a dice roll is probably fair, so the probability of seeing a 4, given that it's even, is 1/3. So the only thing we're left to understand here is what if all the outcomes were not equally likely? And in that case, our intuition doesn't really work. So this is kind of the nuance. Our intuition probably gives us the right answer if all the outcomes are equally likely, and when they're not equally likely, our intuition usually fails. All right, so that's the catch. But instead, let's just replace our intuition with a mathematical definition for now. So the conditional probability, which we're going to write as P of A vertical slash B of event A, given that event B occurs, that is defined to be the probability of A given B is the probability of the intersection of A and B divided by the probability of B. All right, let's say that again. So when I'm interested in understanding the probability that A occurs, given that I already have learned that B will occur or has occurred, so B is occurring, what's the chance that A occurs? I take the intersection of the events A and B, calculate the probability, and then I divide that by the probability of B. All right, and recall that B will only occur if it has positive probability. So we can't divide by 0. So really what we say is when probability of B is 0, probability of A given B is undefined, all right? Because we're not going to divide by 0. So this question only makes sense if B can occur. And so we know that the probability of B will be greater than 0. All right, intuitively, the way to think about this is that conditioning on the event B is like shrinking or restricting the universe of outcomes down to those only in B. And so given B, the only outcomes we can see are those in A intersect B. All right, so we won't see just anything in A. We'll only see things that are in A intersect B. So here's a drawing. Here's the sample space. Here's A in red, B in blue. And then the thing that we're going to do is just condition on B. And then we're going to be left with a universe which is just a shrunken down universe B. And the only part of A that's left is A intersect B. Okay, so there are other parts of A that now cannot occur because we already know that B has occurred, right? Okay, so that's the visualization we should have in mind, is that once I condition on B, I'm collapsing my sample space down to just a smaller space, which is just B. All right, and that's actually why we divide by the probability of B, so we renormalize the probability. We'll see more of that in a minute. Let's go back to our example. So if we go back to our simple example and we just try to see how does this formula work? All right, so remember what I wanted to calculate was the probability of seeing a 4 and I condition on the event that the roll was even. All right, so that's the word problem that I had. I wrote that as a conditional probability. So that's the probability of the event 4, seeing 4, conditioned on the event seeing 2, 4, or 6, which is the even part. And so I take the intersection of the event 4 with the set 2, 4, 6, and I divide by the probability of the event which has 2, 4, and 6, which is even. Okay, so this is the definition of conditional probability. And so on top, I'm only left with the probability of 4, because that's the only thing that they share. And on the bottom, I can use additivity to write this as the probability of 2 plus the probability of 4 plus the probability of 6. Okay, and we know that the outcomes are equally likely, and there's 6 outcomes, so the probability of 4 is a sixth. I'm dividing that by a sixth plus a sixth plus a sixth, and then I can just combine things. I get a sixth over a half, and then I'm left with a third. Okay, so that's exactly what we guessed, and it's correct. And the reason why we mentioned this before is this is a special case of conditional probability. All right, and the special case is that we are dealing with outcomes that are equally likely. All right, and in that case, the calculations are a lot simpler and they're easier to grasp or guess at, right? So it's easier to do a back of the envelope calculation. And if you're interested, then the simple formula for that is just going to be that the probability of A given B is simply the number of outcomes that they share. So the number of outcomes in A intersect B divided by the number of outcomes in B. All right. So that's how the formula simplifies. And this assumes a finite number of outcomes. All right. Let's go back to our city example from the previous video. Okay, so remember, in that scenario, we had a few cities. So we had Boston, Chicago, Los Angeles, New York, and San Francisco. They each had probabilities that someone might prefer to visit that city over the others. And we were interested in this event of a West Coast city, so LA and San Francisco, right? And we calculate the probability that someone prefers a West Coast city. So now I'm asking, what's the probability someone prefers Los Angeles, given that we already know that they prefer the West Coast? Okay, so this is a conditional probability question. We've already learned that we already know that someone prefers the West Coast, and now we're wondering, among the two cities, what's the probability of LA? So it's the probability of LA given West Coast. So I take the probability of the intersection of LA and West Coast. All right, that's the definition of conditional probability. I divide by the probability of West Coast, which I've already worked out. So the intersection just becomes the probability of LA, because that's the only thing that's shared between LA, SF, and LA. And I divide by the probability of West Coast. Now I can just plug in. On top, I have an eighth. I just look that up. And on the bottom, it's the West Coast probability, 3/8, which I worked out. So it's a third. Okay, what about San Francisco? So before we answer this question, let's just think about it intuitively. Intuitively, it should be the remaining probability, which is 2/3. And that's what it's going to work out to be. So let's do it formally. So the probability that someone prefers San Francisco, given that they already prefer the West Coast, so we already know that they prefer the West Coast, that's the probability of SF intersected with W, West Coast, right? And that's divided by the probability of the West Coast, all right? So that's, again, the definition of conditional probability. So probability of SF, the only thing left in the intersection, divided by the probability of West Coast. And we just look up the probability. So SF has probability 1/4, and we divide by 3/8, and that's going to be 2/3, as we expected. And that turns out to be 1 minus 1/3, the remaining probability. So the probabilities sum up to 1 here. And this is for a deeper reason, okay? So the reason is that once we're dealing with conditional probability, it's actually a valid probability measure. And all of the axioms and properties that we've already worked out for probability measures, they carry over to conditional probability. What that means is that we have the properties non-negativity. So the probability of A given B is always greater than or equal to 0. We have normalization. So the probability of the sample space given B is equal to the probability of B given B, and that's 1, right? So I basically, once I've shrunken the universe by dividing by the probability of B, I've ensured that the total probability in this new shrunken down universe still adds up to 1. And I finally have countable additivity. So for any countable collection, A1, A2, and so on, of mutually exclusive events, if I'm interested in the probability of their union given B, that's the sum of their probabilities given B. Okay, these are the axioms that I had for probability measures. They still apply. I also have the complement, so the probability of A complement given B is 1 minus the probability of A given B, and I have the inclusion-exclusion rule, and that's that the probability of A union B given C is a probability of A given C plus probability of B given C minus the probability of A and B given C. And that's an important thing to remember when you're dealing with conditioning, is that usually it will propagate to everything once you expand terms, right? So you'll see that again and again, but that's just something to note here. Okay, so how does conditional probability show up? So one way it shows up is that it's often a lot more intuitive for us in terms of writing down problems to specify all of the probabilities. So to tell you the probability measure using conditional probabilities directly. Okay, here's an example, going back to what we had before. So let's say that A is the event that an aircraft is present, and B is the event that our radar issues an alarm. All right, so let's start on the left with the whole sample space. That's this point here, and I'm going to expand that going up and down in this tree, and on top I have A, and it has a probability of 0.1, and that's the event that the aircraft is present. So now I've told you with this diagram that the probability that an aircraft is present is 0.1, and therefore the probability of A complement, which I'll write on the bottom here, has to be 0.9, which it is. Okay, so this is my way of describing the setup to you. This is not something that I'm solving. I'm just telling you these probabilities via this tree. Okay, and now I want to fold in the event B. The way I'm going to do that is I'm going to use conditional probability. So I'm going to tell you that I have these branches. So this is the event that it's not present. And I have these branches going up to A intersect B. And I can tell you the probability of B given A is 0.99. All right, so this is not directly the probability of A intersect B, but it's the probability of B given A. All right, let's go for the next thing. Then I have on the next branch A intersect B complement, and probability of B complement given A is 0.01, right? And then on the bottom, I'm going to do A complement intersect B and write down its probability. So I have 0.2. And finally, A complement intersect B complement. That's probability of B complement given A complement is 0.8. Okay, so the way that I can use this tree, so now I've specified all of the branches of this tree, which is a conditional probability tree. The way I can use it is if I'm interested in understanding the probability of an event at the right side, I just multiply my way to it starting from the left. So as an example, oh, and before I do that, let me just tell you that we often call these two events here in the middle. So A intersect B complement is usually called misdetection, and that's because the aircraft is there, but the radar did not issue an alarm, so we missed it. And the false alarm is when there's no aircraft, so A complement, and we did issue an alarm, which is a false alarm. That's just some nomenclature for later. So the probability of A intersect B, I get by multiplying from left to right. So I have 0.1 times 0.99, meaning that I have the probability of A times the probability of B given A. And when I work that out, that's 0.099. All right, so I multiplied 0.1 and 0.99, and I got to this leaf on this tree, which is A intersect B. Same thing, I can get the probability of A intersect B complement, probability of A times probability of B complement given A, and that's 0.1 times 0.01, and that's 0.001. I can keep doing this, right? So I just multiply my way down. I get 0.9 times 0.2, that's 0.18. And I can get the last branch here by multiplying 0.9 times 0.8, and I'm going to get 0.72. Okay, so what I've done here is now I've specified the probabilities of all these intersected events, A intersect B complement, and so on. And I could have specified those probabilities directly from the start, but that's a little less intuitive than what we've actually specified. which is the probability that the radar works correctly when the aircraft is present, and the probability that the radar works correctly when the aircraft is not present. Those are more intuitive things to think about and talk about rather than these intersection events. So conditional probability trees are often useful just for description. This is a special instance of something that we actually call the multiplication rule. So the multiplication rule is that if I have any events that I'm interested in, so let's say I have events A1, A2, and let's say a finite number of events up to AN, then if I try to take the probability of their intersection, so intersect A1 up to AN, I can just multiply these conditional probabilities. So probability of A1 times probability of A2 given A1 times going all the way up to the probability of AN given the intersection of A1 up to AN minus 1, okay? So that's the multiplication rule. And by the way, before I explain this a little bit more, I'm implicitly assuming here, right? So I'm implicitly going to assume that the intersection of A1 up to AN minus 1 has positive probability, so that in fact these conditional probabilities are well defined. Okay? And let's look at this in a special case. So let's say I have two events that I'm interested in, two events that I'm going to call A and B, and now I want to understand the probability of A intersect B. Well, I can just take the probability of A and multiply it by the probability of B given A, right? So looking at this rule above, that's like thinking of A as A1 and B as A2. And then I only have two events, and so the probability of A times the probability of B given A. I could also expand it the other way. So I could take the probability of the intersection is the probability of B times the probability of A given B, right? So I can instead take B to be A1 and A to be A2, meaning that I can condition events in any order, even though there I've written it as just a single ordering 1 up to n, but you can do it in any order. All right, let's apply this to kind of see what's going on and where I might use this. Okay, so what I'm going to do is I'm going to draw 3 consecutive playing cards. Okay, so from a standard 52 card deck, and I'm interested in calculating the probability that all 3 cards are hearts. Okay, so let's let AI be the event that the ith card is a heart, and the probability of A1 is just going to be 13 over 52, right? So there are 13 hearts out of 52 cards, which is just a fourth. So the probability of A1 is a fourth. So what about the probability of A2 given A1? Well, this is something we can just intuit because I've taken 1 card out, right? So I only have 12 hearts left, and there are only 51 cards left total. So the next probability should just be 12 over 51. And finally, the probability of drawing the third heart, given that I've already drawn 2 hearts, should be 11 over 50, because now there are 11 hearts left and 50 cards total. So if I'm interested in the probability of A1 intersected with A2 intersected with A3, so the probability that all 3 cards are hearts, I just multiply these 3 things together according to the multiplication rule. Okay, so I get 13 over 52 times 12 over 51 times 11 over 50, which happens to be 11 over 850. Okay, so that's an application of the multiplication rule. Another technique that we use in conditional probability is the law of total probability. So let's say you have a partition, B1, B2, and so on, and every event in this partition has positive probability. Then I can write the probability of any event A in terms of the sums of the conditional probabilities of A given BI times the probability of BI. Okay, so why does this work? Well, if I look at the term inside the sum, so if I have the probability of A given BI times the probability of BI, by the multiplication rule, that's the probability of A intersect BI. Okay, so then when I'm looking at the whole summation of these terms, then I can just replace it with the summation of the probabilities of their intersections. And now, by additivity, I can write that as the probability of the union. And that's just the probability of A. Okay, so why was I able to use additivity here? Because the B's form a partition, then I have mutual exclusivity, and then I can push through the sum to be the probability of the union. And because I have that the B's are collectively exhaustive because they form a partition, then I know when I'm taking this union, I have covered all of A. This is easier to see with a picture. So here's the whole sample space. And I'm going to draw my partition with these rectangles. So I have B1 and B2 and B3 and B4 in this example. Okay, and A is just some arbitrary event, and it just covers the space in some way, and it crosses these partitions in this case. So what I end up doing is I'm just calculating this piece by piece. So I have the probability of A intersect B1, and I'm adding that to the probability of A intersect B2, and adding that to the probability of A intersect B3, and finally of A intersect B4. So when I add all of those up, I get the full probability, or the total probability of A. All right, let's do an example. So let's say I have a part, and I have manufactured this part using 2 3D printers. Okay, one of these printers I know to be slow and reliable, so it produces parts of high quality, and the other one is quicker, but the quality of the parts is a little bit lower. Okay, so let's define the events that A, the part works after a year. Okay, so I'm using the part in some system, and it's still working after a year. And let's say that B1 is the event that the part is from a slow, unreliable printer, right? It's from the slow and reliable printer. And let's say that B2 is the event that the part is from a quick but unreliable printer. Okay, and in this case, we're going to think of B1 and B2 as a partition. And so the probability of B1, we're just going to declare to be 1/3, and the probability of B2 declare to be 2/3. Okay, so that's a partition. And the probability of A given B1 is 9/10, and the probability of A given B2, we're going to say, is 7/10. Okay, so this is all the information that I need to determine what is the probability that a part that I've manufactured, and it could have come from either printer, what's the probability that a part works after a year? All right, so the way that I get at this is I just say I'm interested in the probability of A, and I just take the probability of A given B1 times the probability of B2 plus the probability of A given B2 times the probability of B2. That's the law of total probability. So it's just 9/10 times 1/3 plus 7/10 times 2/3. Okay? And so then I get 9 plus 14 over 30. And that's it. So I just get 23 over 30. So that's a quick application of the law of total probability. Finally, let's talk about Bayes' rule as our third technique. Okay, so this technique I want you to remember as a way of flipping conditioning, meaning that let's say that the thing that you actually have access to is the probability of A given B, and you want to know the probability of B given A. So you want to flip A over to the left and B over to the right, or vice versa, right? So let's say I want to know the probability of B given A, and I know the probability of A given B. I multiply by the probability of B and divide by the probability of A. Okay? So that's it. So if I want to flip conditioning, then I take the probability of A given B, multiply by the probability of B, and divide by the probability of A. Why does this work? Well, the probability of A given B times the probability of B is the probability of A intersect B by the multiplication rule. And by the definition of conditional probability, probability of B given A is the probability of A intersect B over the probability of A. Okay? So with that in mind, what I've done here is just reproduce the definition of conditional probability. I just happen to be writing the probability of the intersection using the multiplication rule. The main thing to remember about Bayes' rule, rather than the specific formula, is that in general, we do not have that the probability of A given B is the probability of B given A. All right, this is generally not true. All right, and it's very easy to get a bit careless and make mistakes in this way. So the main thing to remember about Bayes' rule is it's there, and it's our way of flipping conditioning rather than forgetting and pretending that the two terms would be equal in this case. And it's often useful to combine Bayes' rule with the law of total probability. So let's say I have a partition B1, B2, and so on, and all of the probabilities are positive so that I can use the law of total probability. And so the probability of Bj given A is the probability of A given Bj times the probability of Bj divided by the probability of A. That's Bayes' rule. But what if I don't know the probability of A given the information in my problem statement? Well, one way I might be able to get it is just by using the law of total probability. So what I've done here is I've replaced the denominator with the sum of the terms, probability of A given bi times the probability of bi, summing from 1 to whatever I have. In this case, infinity, but maybe just up to some finite n. All right, easier to understand through an example. So let's go back to our biomedical engineering example. So let's say I'm testing for disease, and the disease is rare. This is a rare disease, and my test happens to have come back positive. Okay, so I have a patient, I've tested them, comes back positive. What is the probability that the patient actually does have the disease, right? So maybe I had a false positive, maybe I didn't. What are the chances? So let's define the event A, that the test is positive, okay? And let's say that the event B is that the patient actually has the disease. And it's important to define these in terms of A and B so we can go back to that definition and see clearly what we should use. So the test is going to be correct with probability 0.95. So this is part of the problem statement. So I'm just telling you that you have access to a test that's correct 0.95 fraction of the time. So what does that mean that it's correct? Well, what it means is that when you have the disease, it says positive with probability 0.95, and when you do not have the disease, it says negative, again with probability 0.95. So that is one part of this problem you could get a little confused on, that this is actually specifying two separate terms here, just this idea of it being correct. Okay, the other thing that I need to know is what's the probability of actually having the disease? So what's the rarity of this particular disease? So let's just say that in this case, the probability of a random person having the disease is 0.00001. So 4 zeros and a 1. And so I just write PB is 0.00001. So what we want to know is the probability that the patient has the disease given that the test is positive. So the probability of B given A. And so using Bayes' rule, that's going to be the probability of A given B times the probability of B divided by the probability of A. That's what we just learned. Okay. And we just looking at this for a second, we can see that one of the terms that we already have is the probability of A given B, that's 0.95, and I have the probability of B, but I do not have the probability of A, and this is how I'm going to use the law of total probability, which is often useful in conjunction with Bayes' rule. So I'm writing the denominator as the sum of the terms the probability of A given B times the probability of B, plus the probability of A given B complement times the probability of B complement. So that's the law of total probability. I'm using B and B complement as a partition. And that's a nice thing to remember, that any event and its complement always form a partition. Okay, now I can just plug in numbers. I have 0.95 times 0.00001 divided by the same thing, right? So I just plug in again the same product plus 1 minus 0.95. So why do I have that? Because the thing that I'm actually given is the probability of A complement given B complement, not A given B complement. So I need to use the complement property. Again, and I also have the probability of B complement by taking 1 minus the probability of B. So I plug all of those in, and now I'm just going to do a little bit of calculation. Maybe you want to find a calculator for this or not. It's kind of up to you. So I have 9.5 times 10 to the negative 6 is one term, and 0.049995. And then if I just, again, plug that into something, I'll get 0.0001896. Okay, the main thing to remember about this is that it's still very low, which is a bit counterintuitive. So what's happened is I've refined my understanding of whether or not a patient has the disease using this test. But since the disease is quite rare and the test is not correct enough with probability sufficient to give me a lot of confidence here, they may still not have the disease. In fact, it's more likely than not that they don't have the disease, right? So the chance is a lot higher that you got a false positive and they don't have the disease than you got a true positive and they do have the disease, because the disease is quite rare. And Bayes' rule is a nice way of accessing those kinds of ideas which don't come so easily to our intuition. So this is something that, if you're ever visiting a doctor to get some kind of test, you're hoping that they have this in the back of their heads and that they kind of pick this up at some point in their training. but now you know it, so you're in a good position to start evaluating these kinds of ideas. And that's it.